Hello. Morning. All right. Yeah, we can get started. Okay, so good morning. Welcome to the meeting. So this week we had our DevoWorm meeting, of course. We didn't have an open source meeting this week, but we did have updates from the students. We had Sarah, of course, and we had Hough, who's doing open source, sort of an open source scholar, is not being funded by GSOC. And they're doing some really interesting work on the different forms of this open source sustainability. So simulating open source communities in different ways. So Sarah, of course, is doing the large language models, and Hough is doing something with multi-agent reinforcement learning. And so they're both coming along pretty well on their projects. The multi-agent reinforcement learning is really interesting because we've been working on the reinforcement learning angle of that for a couple years now. So we hopefully will have, by the end of this summer, some really interesting work in that area. But also the large language models work is very interesting. And so Sarah's been really kind of making that happen. I'm really impressed with some of the work she's been demoing in the meetings and making pull requests. So she just made another pull request yesterday. So thanks to Sarah for that pull request and the pull request she's made so far during GSOC. And speaking of GSOC, we've just passed the first evaluation. So I've been evaluating not only Sarah, but the students in the DevoWorm group as well. And everyone passed, so congratulations to them. And that's Pocky and Mehul. And so we're looking to get back into the swing of the cybernetics meetings, as well as the cognition futures meeting. So the cybernetics meeting we held off on last week because it was the 4th of July in the United States. This week, we didn't have time for it. And so we're going to try to get back in the swing of things soon. So that's good. Okay. So, yeah, let me get to some of the things that we have here for today. So the first thing is that, yes, I just mentioned that Sarah Bastawala has been working on this large language model framework for GSOC, for open source, to model open source communities. She's been posting on our Medium. She's posted the last 4 blog posts on our Medium. So we have these different updates that she's given on the project. So she kind of, in the first one, highlighted from reinforcement learning to large language models. Then sort of her reflections on our community period, and then the building blocks for her approach, and then the midpoint milestone. So this is the latest post where she talks about using LLMs in this framework, in this larger framework. So this is the sort of using Olama and Llama models. So this is so she talks about using large language models, exploring those, sort of the recap of the previous work, and then creating this open source community environment where you can deploy agents that are large language models. What the large language models are going to do is go through a lot of the sort of the process of a contribution. So like, looking for issues, addressing issues, working as both a contributor and a maintainer, and doing all that. And so that's the kind of thing we spent a lot of time 2 years ago on trying to figure out the sort of the how to measure those things in open source communities and how to characterize them in an agent-based model. So this is definitely, something that we can always benefit from going over again. But, she's made some pretty nice advances in this. So looking at different algorithms to use to sort of characterize these multi-agent systems and how people might behave in an open source community. So you have the authoritarian model versus the decentralized model. This is, of course, if you go to different open source communities, Some are very authoritarian, some are what they call benevolent dictatorships, and some are rather decentralized. And, without accounting for disruptive and bad behaviors or, ego trips or whatever you want to think of. You can think of a lot of examples of that in open source. These are basically models of, when you have different types of governance. So if you have the authoritarian form of governance, where you just have one person making decisions for everyone, or decentralized governance where people always vote on everything. Now, most open source communities are somewhere in between this. So, but nevertheless, these are good models just to kind of take it as a way to sort of characterize, different styles of governance. And so this is a nice post. Thank you, Sarah, for making that contribution and all the contributions you've made to both GSOC and to the project, the pull request, and or Medium, which is always looking for content. So it looks like we have Jesse here today. Hello, Jesse.
Good morning.
Morning. Okay. So I guess I could ask if you have an update or if you're
Essentially, the answer is no, because I've actually been on sort of a real vacation last week, which is nice and very different. But even on my vacation, I've stumbled into some interesting things. One of them is I attended a workshop on polyvagal theory, which is sort of in the space of kind of social work, kind of like clinical social work or regulatory. Not really. I don't really know if it's psychiatric stuff, but psychology, social work space. And at its core, it's about regulation of oneself. And I really like the teacher. The teacher was Deb Dana, who's been a social worker for many, many, many years and does like clinical work and counseling and all this stuff. But there's also, I think it's Steve Porges who does the actual research and is working on also making sort of biometric like tools to study, in the case of the theory, the different states of the theory. I'm not going to go into what the theory is right now. I am positive about some applications and agnostics about others, but it was very interesting to tie it directly to the lab. It's very interesting to consider in terms of the sort of phenomenology quest line that the Christian Futures group has gone on. There were some pretty direct ties to maybe things like microphenomenology or cardiophenomenology in terms of getting an individual to sort of understand or demarcate aspects of their experience. And in polyvagal theory, there's some really, for general categories. And it's a very simple, mapping of different states or different sort of motivations. But I really liked the course I attended was a pretty general, it was very interesting because I think there were many people who are like longtime practitioners of physical therapy, clinical social work, which is the more individualized. For those that don't know, like clinical social work is when you have people and you counsel, you're like, there's like direct interaction with individuals. There's also like meso and macro social work. But this is, Deb Dana is a licensed clinical social worker, I believe. So she has a lot of just like hands-on experience with leading people through that stuff. And I think what I'm realizing kind of through all of this is like that space hasn't always had, one of the things that I've talked about in sort of the mental health working group and in here maybe less with the language I'm using currently, but there's kind of been these emerging a lot of things that have developed in the space of like what is social work or psychiatry or psychology or cognitive science or the whole like person studies arena. There's been developments in these spaces across time, but many of them are just quite siloed. So what's an appealing angle to look at here is how in it like no one said the word phenomenology at all during the whole work of the whole workshop, but it was indirectly like it's what it was about. And see if I can find. I've picked up a small book from the library about like child development and polyvagal theory, which might be an interesting bridge between some of the developmental aspects of that. Some of it was very very like technical and research. And I have no particular like background in any of this. So I mean, it's in essence, it's this sort of applied update to the idea of the sympathetic versus the parasympathetic nervous system into a nervous system that's sort of regulated or not in the ventral nervous system, and what part of like the vagus nerve and vagus system is sort of being more active than others, or what, things like that. And I'm very agnostic and don't have an informed or full opinion on, some aspects of that. But it's been interesting to think about in terms of our investigations into, like, can phenomenology and sort of the Varelian quest line to get a little bit more of an informed or scientific take on subjective or personal experience. I think there's something interesting. There's some interesting things there, and especially the work of Steve Porges, I believe that's his name, who has founded it and is still doing research and trying to make like devices around it in his lab. He's at Indiana, and there's a lot of stuff there that everybody else, you all know more than I do about that, but I'm quite curious to look into it. I haven't had any time because I've been on doing a bunch of vacation stuff, but it was very exciting in that sense. So that's something that like I definitely want to look more into and kind of see where the research is, because that's the book I picked at the library was, maybe it was 2020. It looked a bit older, but it might have been just been 2020. But just like applied to child development, which is might be an interesting bridge between some dev AI stuff and our general developmental focus, and then this other thing. And I really personally do like the applied version of polyvagal theory that Dana led through the workshop, but I'm not sure. I don't know yet what to think about the enterprise as a whole. But it was a nice kind of fun. I didn't plan to walk into that over my last week or so, but I did, and I'm happy to do that. Happy that it happened mostly. So that's sort of one update. I don't know if there's any questions or comments about that before I move on to some other stuff.
You could move on. I have some ideas, but I'm not quite yet sure what they are yet. So.
Yeah. Other things on the docket of continuing a very long, slow process of updating some things for JoPro. I think I'm almost there. I think it's so much work just to do so much small things, even on like a website. I really just wanted to shift the website being hosted from like Google Sites to another host, and doing that the right way has taken quite a long time. It's been interesting to compare to other groups and sort of the path of taking what I want to do with JoPro in a presentational or just a general sense to like other groups that are trying to do incubator type things. like one comparison that I like, at least aesthetically, but I'm obviously nowhere near in reality, is sort of what the Media Lab is doing, and how the Media Lab at MIT is basically just a bunch of these sort of, it's almost like a bunch of just independent states in the United States way, but independent labs that are, much more fun than I'll ever have any fun in doing anything. So it's like I'm acknowledging that's not going to happen. But the presentation of it and the way they kind of have this federation of different things, I think is really cool. At least it's kind of, honestly, I'm realizing how confusing their website is and how much their website has a lot of details that you won't know until you pay attention to, which makes sense in a lot of ways for what the lab is, what MIT is. But I've been like, between that and some things that Effective Altruism has been doing for their like their mentoring stuff. They're kind of not really competitor analysis, but just realizing when people come to what I'm trying to do with JoPro, what they're going to see, or what their most obvious reference points are going to be, are probably going to be those things. And so, as it stands, JoPro is a humble, fledgling, small group that is trying to support a few products. And I don't think it's really going to be anything more than that ever. I'm not interested in doing that right now, but I'm interested in having a legitimate, I don't know, a little bit, upgrading a little bit what it is in terms of what people can see from it. But hopefully that will basically be, that website update will hopefully come online in the next week or so. And it really will look almost exactly the same, but it will have a much better foundation for things I want to do in the future than what was existing. So that's what the goal is. While I was on vacation, Jen was doing some things for the mental health working group. I know she's been writing about things about Inside Out. One really cool thing, as a side note, would be what if I might write a small post about this, but it's not a big deal. But like, what if Inside Out was actually based on Polyvagal Theory instead of IFS and internal family systems? I actually think it would be much easier in some ways, because the model is much less complicated. Like, it's basically 3 states and sort of 2 macro states of either, are you set, are you eventually regulated, or are you not? And it's a very, very simple, it's not I'm not even sure it's like, I don't know, and I haven't looked in the research, so I can't say, like, as I was taught it, it's not really, like, I don't even know if it has the potential to be academically rigorous to an extent, but functionally speaking, and this is where I think there's some really interesting overlaps to what the Varelian phenomenological investigation line is trying to do. Functionally speaking, in terms of giving a language to people navigating the states, I think it's actually has some substance there. So that's why I'm thinking about, like, almost a sense of what if Inside Out was made with Polyvagal Theory. It would be a very interesting sort of discussion, or at least a bridge point. And I think Inside Out, in the contemporary life of our kind of limited models for anything in this space, is it's a great bridging point. So we'll see about that. Condition Futures didn't meet once again. I apologize. Travel plans have been, I've actually had like legitimate stuff going on the whole time. So, but I'm looking forward to next week being, at least for the cybernetics reading group. I looked a little bit more at the paper, your paper, or our paper, I guess, the World Models 1. I really look forward to getting, like, going through that one totally again. And what else? Other general updates are I have other, I'm trying to just, as I'm back from vacation, it's sort of like that unpleasant, like, it's just slow to pick up where you left off. But
Right.
I left off in the middle of a lot of Joe Pro stuff. I'm realizing I need to update my own website some, which I don't really want to do. I realized like the effort. I'm realizing just the disparity between the effort to create things. Bless you. The effort to create things versus the effort to design stuff that other people are looking at. It just feels so unpleasant to go back and forth between those two
Yeah.
things. Like I wanted to stay and okay, I'm writing intense. Really, I'm really trying to put my all into writing this thing that doesn't exist or words that haven't been said at least by me before, versus designing how things look. And it's like, oh, like you either want to make it like I understand. It's just, I continue to understand why so many academic websites or like people's websites are just so minimalistic or just whatever, because it's not the easiest thing to outsource either. It sounds like I like to make a website to sell some products like on my have a digital marketplace, my business, and sell these products. Like it's not as simple as that.
Yeah.
Um, it just isn't, because how you phrase things is the decision pressure. How are you going to show this? How, even the most basic versions of it are tedious in different ways. So I'm dealing with that, but I'm happy to be back. I'm thinking about okay. I think it's like 50 days between now and September 1st,
Okay.
and I'm just thinking like, what is it that I want to try to do in those 50 days,
Right.
and including stuff, some other summer things to do, but like I really would like to finish. In my high-minded ideals, there's a bunch of preprints I want to like get into preprint status.
Yeah.
So we'll see. Any other updates on my end broadly? Plot twisters is nothing new to say there. Kind of a holding pattern, and thank you for letting the update happen there.
Oh, no problem. Yeah. Okay. I think that's good. So yeah, thanks for that update, Jesse. That was interesting. A lot of I'm not familiar with polyvagal theory. It might be an interesting thing to talk about with respect to development or developmental AI or whatever we're getting at with that. And of course, we'll pick up with the cognition futures meetings when you're ready, and of course these cybernetics meetings. So that'll be fun too.
I think that I'm remembering something right now. Just I'll briefly say, just to mention it. It would be there's some interesting, like essentially bridging from the work that I guess Sarah's somewhat doing now, and the paper that we had that was basically the Sims paper about modeling the Sims town, potential interactions with LLMs and updating that. I think there could be something there as well in terms of like polyvagal theory could have a space there, and also there was something that uh, I, I I think last week or a week beforehand. I don't know if I mentioned it, but Avery actually um, was discussing some of their theories and ideas, and oh, I remember one other thing too. But I think I would really it may even be like a fall or the next year, but legitimate thing that could happen would be putting some of Avery's ideas into essentially the simulator,
Okay.
because Avery has very sort of unique and novel takes on interpersonal, interpersonal management. I guess management sounds a little administrative, but like how states change and how different characteristics play out, so to say. So it'd be really interesting to basically remake that paper with some of Avery's theories. And I think that'd be a really fun thing to do and legitimate. Like I would like to do that. I think it would be pretty tenable to do. Like, it wouldn't. It's one of the things that seems like very much possible. Like as either as a, um, I don't know if we could bridge it all the way into like actually picking up Bradenberg vehicles or some metabrain stuff. I don't know if that would be a bit of a stretch. That would be like an amazing potential future Google Summer of Code type thing.
Yeah.
But in a much more general sense, just basically making the paper happen again with different like personality um, descriptions would be interesting. Um, and there was a few things on that line. Like there's a space for like I don't know what to say, and maybe it's essentially just representation of brains and phenotypes. But I feel like there's there's a version where between all that stuff, Dev AI, well, no, let me back up. Between everything under that general banner, which is sort of brain brick vehicles, meta brains, and maybe developmental AI, and and I guess it bridges a little bit with things that are happening this summer. But I think there'd be something really cool to return. I don't know if the return to is the right word, but for the lab to build out or return to some of its like simulation of interaction approach, because that's something we can totally do. Like this one, we don't need to make we don't need more resources than we have. You know what I'm saying?
Right.
So I think that might be a cool thing to do, and especially if we can combine it with Avery's EverQuest for what they do. That's something that's definitely interesting and appealing, and something I'd like to get more experience in down the road as well. Um, so yeah, um, just sort of making a big point about that, just to say, hey, let's do that. And maybe that's actually let me I'm just gonna write. Give me like 10 seconds,
Okay.
just so I can write my own note on this. Okay. And the last thing, which is pretty minor, I also happened to attend a reading group by Emil Torres, who is the sort of the currently probably most known for being like with Timnit Jabru, a co-author on the TESREAL bundle stuff, like the transhumanist, rationalist, effective altruism, long termism, and whatnot. But I think their home base, as in Emil's home base, is more in sort of studying. Like they've written books on like takes on extinction, or like how people feel about where things are, like where the future is going, or the end of civilizations, or end of whatever, which is kind of grim topics. But I attended a book club with them, and I can't remember the details of it specifically, but it was basically going through some of their uh, it was very philosophy art oriented. So maybe something to talk about Amanda with, but it was just sort of bigger, broader takes on how the future is evolving. It was quite interesting. Um, it's it's always interesting to see. Um, it's always interesting to think back to the Princeton Vision time, where Phil, Logan, myself, Avery, uh, Angela, and some other people were all together, and we've all kind of branched out in different ways. And I think Emil and Logan are both deeply concerned about the future in different ways. Uh, and it's kind of interesting because I think I'm somewhere in the middle between them, whereas Emil is very grim, not grim dark, but like grim hope. Like, let's look at all these really negative things and sort out where they're coming from. Whereas Logan's very, very, no, we need to talk positively about the future. I think they're both right in different ways. but it's interesting to kind of see to see this group of this sort of, I don't know, the class of Princeton and Vision 2019 and all the things we're trying to do in the world since then. So yeah, I deeply appreciate all of those people and being able to see where they're going. Logan posted something recently also, but I don't have anything great to say. Like I can't think of it clearly enough to talk about it. But I know there's some things with the Foresight Institute that he's looking to do or has done that I want to try to do next week. I think there's some event coming up that him and or my friend Dan are trying to do. But more about that later. So that's it. Those are my updates for the time being.
Okay. Well, that's great. Yeah, it sounds really interesting. And yeah, following up on some of that sort of futurist stuff too. It's interesting. Yeah. So why don't I move on to some other things? Actually, this coming week will be the NeuroAI course for Neuromatch. So,
oh yes,
Neuromatch is of course happening this year. They have now, I think, at least 3 courses. They have the deep learning course, the computational neuroscience course, and the NeuroAI course, which is brand new. So I'm going to be mentoring for the NeuroAI course. And it's, like what I've done every year where students will have projects. I'll meet with them, I think twice to sort of mentor them on their projects. And they'll go through the summer school, which is like a series of topics that they'll do a crash course, like a 2 or 3 week crash course in. And then they do the project, and then they present on their project at the end of the course. So given that the NeuroAI course is a new course, I figured we'd look through what they have on their syllabus. So this is Neuromatch's website. This is the NeuroAI course. This is a brand new course this year. And of course, NeuroAI is where you have the neuro, which is the neuroscience, the computational neuroscience, the models of the brain, the models of behavior, and then the AI, which is the artificial intelligence part, which is where you have, simulations of behavior, simulations of, things models that you train and they produce output, large language models, deep learning, whatever. And so the idea behind that is where you want to be able to look at these 2 things together, maybe with some bio-inspired models as well. I'm not really sure how they're going to approach this at the very technical level, but they have some data sets like they do for the computational neuroscience course. They have some basic topics that they're going to go over, so let's see what they have. So this is a 2-week live instruction course, so it's actually 2 weeks. I believe the deep learning course is 3 weeks, or the computational neuroscience course as well. But that's, they always keep changing it and tinkering with it. So this course is aimed at a more advanced audience than our other courses. Students should have already taken our deep learning and computational neuroscience courses or the equivalent. So I think this is for people who've taken both of these or at least one of these. And, they kind of want to go over topics more in depth, given that sort of base of knowledge. So the NeuroAI course, the motivating question is, what are the common principles of natural and artificial intelligence, so the natural intelligence systems and the artificial intelligence systems, and then sort of find common principles between them. So, a lot of the NeuroAI I've seen is not really, people haven't really come up with these common principles. It's sort of maybe a goal, but a lot of the stuff is largely, that at least I've seen, has largely been around, focused around applications of maybe like, some maybe predicting V1 activity with a neural net or something like that. And then, of course, the idea is that you get common principles from that. But the common principles, we don't really know what those are. So that's what we're trying to get at in the And usually, when you teach a course, you kind of ask the question, and it's kind of rhetorical. You maybe know the answer somewhat, or you are trying to find out more, but that's usually a graduate level course where you can unpack things with discussion. This is more of a summer school, so it's interesting that they're approaching it this way. The core challenge of intelligence is generalization. So this is what they define as the core challenge of intelligence. So it's basically learning things and then generalizing from the training set or from that body of knowledge to other things. Neuroscience, cognitive science, and AI are all questing for principles to help generalization. So this is again, I guess that's true. I mean, cognitive science, I'm not really sure that that's the same as what they're trying to do in AI. Same thing with neuroscience, but that's the way you put these together. Major system features that affect generalization include task structure, like multitasking, multiple inputs with same output, and vice versa. So multiple input, multiple output systems. Basically where, you go beyond the single input, single output system. And so microcircuitry, nonlinearities, canonical motifs in their operation, sparsity. So this whole area here, where you're looking at small circuits, you're looking at their dynamics, their behaviors, their structure, and some of the attributes of those circuits. So we know, for example, that we can get intelligence out of circuits that are relatively simple, or sometimes circuits that are relatively hard to see the structure. And so this is all kind of what we're interested in. Is this what's the secret sauce of this circuit? If we can boil it down to a circuit. So there's microcircuitry, there's macrocircuitry or architecture, and this includes modules for memory, information segregation, weight sharing by input symmetry or common development. So this is an interesting. This is actually, in particular, an interesting statement here: weight sharing by input symmetry or common development. So this is something we're doing with developmental AI. I don't have it with me, but there's a paper I'm working on developmental Bradenburg vehicles and sort of the morphology of the vehicle, or the sort of the symmetry, relative symmetry and shape of the body, especially as it changes in development with respect to some external stimulus and then an evolving nervous system network. So this is an interesting question for my interests, but also for the lab and more generally. In any case, that just shows you where we fit into this. Learning rules, synaptic plasticity modulation. So, when we're dealing with synapses, we could have just simple weights. We could have weights with rules. Then we have to also deal with plasticity. We have to deal with modulation. So these are things that kind of go beyond what we have in, typical deep net architectures, for example, where we just have a matrix of weights. We'll have a matrix of weights over time, but those weights are sort of governed by certain transition rules or, dynamics that we don't usually put into the models. And then they also have data stream, and the word they use is curriculum. So this is like curriculum learning or curriculum training or autocurricula, that theme in the machine learning literature. Okay, so there are a bunch of really interesting issues around NeuroAI. They're kind of unpacking a lot of the sort of the basics of the field. So this is an interesting kind of set of approaches. I mean, you could argue whether this is the totality of NeuroAI, whether maybe we should talk more about bio-inspired systems or whatever, but this is at least, I think, a good start. We aim to present current understanding of how these issues arise in both natural and artificial intelligence, comparing how these system features affect representations, computations, and learning. We provide case studies and coding exercises that illustrate these issues in neuroscience and cognitive science and AI. So across these three fields, neuroscience, cognitive science, AI, one is dealing kind of with the mind, one is dealing with the brain, and one is dealing with artificial applications of that, although, AI has traditionally not really been that closely tied to neuroscience and cognitive science, at least the sort of experimental work. That, AI is sort of a cognitive science, but, you know, uh, it's a, how that goes. You get, you start to drift away from your cognate as you sort of develop your own agenda. Yeah, there you go, +1. So there are 3 learning goals for this, or actually 4 learning goals for this workshop or the summer school. Learning goal number 1, a common understanding of vocabulary to describe changes faced by naturally intelligent systems. Or challenges. Okay, so learning goal number 1, a common understanding of vocabulary to describe challenges faced by naturally intelligent systems. So it's this common understanding of vocabulary, describe core concepts, describe core shared concepts in neuroscience, cognitive science, and machine learning, and how they differ from each other. Describe and implement different ways in which an ANN can be compared with the BNN, the ANN being the artificial neural network, the BNN being the biological neural network. Then describe multiple scales of computation and multiple scales of study. So in this case, they're thinking of Mars levels, or what, how, and why, which is sort of the Tinbergian view, and kind of bringing that together into a single sort of framework for looking at intelligence. So again, Mars levels are these different levels of explanation. In the Tinbergian view, you're asking how and why something is useful, both developmentally and evolutionarily, and proximally and distally. And so you get this model of sort of level of explanation and also function and structure. So that's good. This is, I guess, the way I see this is like they're trying to really kind of synthesize the field, because there doesn't really exist a very strong synthesis. So you're teaching people something about the synthesis, but it's also an incomplete synthesis. So you're trying to encourage them to think about like how to bring those things together. It's an interesting learning goal. We'll see how it goes. Learning goal number 2, experience a multiplicity of approaches and interests at the intersection of neuro and AI. Be able to describe some of these approaches and interests. That's good. Learning goal 3, be able to practically implement NeuroAI models. So this is basically just standard, going technical demos, going through how to do something, coding and training models, adding more features to existing models, debugging within guardrails, interpreting, analyzing, critiquing existing models. So this is just implementing debugging models, which is of course important, and then being able to sort of critique models and their shortcomings. This is an interesting learning goal. I don't know if they can do this in like 2 weeks though. This is tough because I guess this is what the projects are for. And so, you're going to have to do all those things in the project. So having a practical aspect of it is nice. But it's like, that's something that as an instructor of technical subjects, I know that you can only, you have to really kind of constrain how people spend their time on this. Like, you could have them do a practical implementation. It could take them like 100 hours. And that's not something that's practical for a course, especially a 2-week course. So, getting those sort of, examples, the sort of laboratory exercises, those practical exercises, down to a manageable piece is always a challenge. And then learning goal 4, complete research that deals with difficulties in NeuroAI. So this is an interesting point. This is research that sort of, if you can implement something, it's always going to be difficult. This is not something that people, there's a research field in NeuroAI, but really the applications are not quite there yet. So that's the thing that they're getting at here. Can you try to implement something as a NeuroAI application? If you can't, why can't you? If you can, how hard was it? And they say that knowing that it's not an easy lift, because we don't have really good models that are, sort of this NeuroAI approach. It's just kind of bringing things together and seeing if they work. So a lot of this is actually posing and solving problems. So the first part is writing down a problem in a way that makes it tractable, interacting with other people from other disciplines, do research, read papers, implement previous state-of-the-art, and then communicating their research in ways that are comprehensible. So this is all kind of working in an interdisciplinary fashion from from AI, neuroscience, cognitive science, and then figuring out kind of how to write out a problem that is solvable and can be solved in 2 weeks to at least some degree of satisfaction, and then also bringing these fields together and implementing something and getting it to work. That's a lot. It's a lot of stuff in 2 weeks. But this is, I think, very useful, and there's going to be a lot that you can learn from this. So we have open source content again. This is the NeuroAI course content on GitHub. So there's a GitHub repository for this. We haven't forked it yet. I'll have to fork it later. But this is the syllabus. So it looks like we have a lot of contributors here to this repository. We have the book, which is the Jupyter book. This is where you have all of your sort of demos and things like that. Prereqs. So I guess the prereqs are just like different, neuroscience familiarity, programming, knowing PyTorch, deep learning, math skills, basic stuff like that. I think the requirements are similar to the deep learning course. The projects that's, kind of working on, we'll probably fill this in. There's the keynote in the Jupyter Notebook format. So this is kind of going over, this is actually a climate-based keynote. So this is, I don't know if this is filler, but this is basically, it's an interesting sort of approach because you're kind of giving code for the slides, code for the video here. It's interesting. I don't know what they're doing here, but and then of course we have tutorials, and these are all kind of for these different areas. So you have modules, schedule, technical help, you have generalization, comparing tasks, comparing artificial and biological networks, microcircuits, macrocircuits, neurosymbolic methods. We've talked about that. Microlearning, macrolearning, mysteries. I don't know what that is. But this is their agenda for the 2 weeks. So week 1 will be generalization, comparing tasks will be day 2. Day 3 is comparing artificial and biological networks. Day 5 is microcircuits. So day 4 they didn't have on here. The second week, macrocircuits is day 1. Neurosymbolic methods is day 2. Microlearning is day 3. Macrolearning is day 4. And mysteries is day 5. And I wonder what mysteries is. So this kind of goes through, well, they don't have, I guess they have the tutorials in here, the intro and the outro. I'm just curious what these are. I guess they don't have them really ready yet, but yeah, they're going to have, well, they have the video, they have feedback, and they have slides. So I don't think they're quite have everything populated yet. But that's the breakdown of the course. So that's the breakdown of sort of the learning goals, the curriculum, and then this is a thing that kind of puts the curriculum in a context. So you have this sort of quadrant system where you have applied AI, applied artificial intelligence at the top left. And that involves mining neuro to find new AI. So that means that you go back to neuro and you look at what people were doing and you try to find interesting AI in them. So there's all sorts of stuff like predictive coding, perceptrons, reinforcement learning, attention, and Turing tests. And those are all things, I guess, I don't know about the embodied Turing test. So those are all things that you look at neuro and you see what people are doing, the major themes, and then you bring that into AI. Using neuro data as realign AI, meaning that, I guess, you can use neuroscience data to improve your models. You have things like biologically inspired perceptrons, biologically detailed modeling, cognitive architectures, and neurosymbolic AI. That's all in applied AI in that box. There's clinical neuroscience, which is in this quadrant. You have things like digital twins plus AI to optimize treatments, foundation models for neuroscience, AI-based health biomarkers, and I think they don't really have enough to fill this out. But there's also AI tooling, like computational ethology, which is animal behavior and looking at that computationally, dynamical models, spike sorting, decoding, and BCI. That's all in this clinical neuroscience bin. Basic neuroscience, AI as models of the brain. So this includes like looking at different types of models and how they sort of approximate different things in neuroscience. So for example, the ventral stream of the visual system can be characterized by a convolutional neural network, or a dorsal stream of the visual system, which is the one that goes over the top versus over the bottom of the brain, is 3D convolutional neural network. Hippocampus equals a transformer, so they view the transformer as being equivalent to the hippocampus. Reinforcement learning is equivalent to the basal ganglia, which is a series of centers in the brain that model motivation and movement behavior and so forth. Wave to vec is equivalent to the auditory system, and then grid cells, which are equivalent to some sort of navigation model, which we don't have defined yet. So you can see there are a lot of missing parts here, and the point is to bring those together, either through learning or through kind of like doing this course a number of times. And then there's theoretical AI, so there's a lot of stuff sort of at the boundary of basic neuroscience and theoretical AI. Some of those include animats, which are simulated animal models, plus brain AI hybrids. So you have a lot of stuff from artificial life and from the area, but there's a formal area called animats, but it's basically artificial life stuff. Biologically plausible backpropagation, so this is where we take concepts like backpropagation and try to find more biologically plausible mechanisms. Adversarial attacks, theoretical deep learning. Those are all kind of on the boundary. And then theoretical AI being pure theoretical AI, which is where we use neural tools to investigate DNNs. And so this is where we look at things like circuits, psychophysics, preferred stimuli. And then geometric deep learning sort of exists at this boundary between applied AI and theoretical AI. And there are a whole bunch of things, like graph neural networks I think would be there too, where you go between like kind of theoretical AI and applied AI, where you're looking at the networks. And actually, if you wanted to throw some neuroscience into that, you could say, okay, we have graph neural networks that represent like the connectome, and that graph neural network has like this theoretical aspect and this applied aspect where we're actually trying to get some results out of it. So that's sort of like the neural developmental programs that Pocky is working with in DivaWorm. We have these networks that grow, these networks that you can describe theoretically using some sort of network model, and then you want to actually implement them and get them to process information. So that's what we've got. We've got this really interesting curriculum. We've got this really interesting set of questions. And that's what's going to be happening the next 2 weeks online. And so I'm going to be mentoring for the projects part of that. I don't know what the projects are. The students have to come up with them. But I think, we should revisit some of these topics, especially with respect to some of our interests. It's a nice way to kind of bring NeuroAI, into focus. Are there any questions or comments about that?
It looks interesting. I forget if I don't think I ever officially signed up for this one, but NeuroAI I think is the one I haven't done yet.
Yeah.
And had I known that my summer would be the way it is, I might have tried to do it. But it does seem like it'd be really interesting to see what they do in the 2 weeks. You know, Neuromatch is always. Are they all the courses are 2 weeks now, right? I think when I did it originally, it was 3 weeks.
Yeah,
Is
I
that
think they may be shifting, but this is actually a new course, so they might just try to be, trying to condense this one down a little bit. So,
It's a ton of stuff as always. Whatever.
yeah.
2 or 3 weeks doesn't really matter. It's like it's going to be not enough. Um, but that's still good. If I'm feeling ambitious, I might try to mirror a little bit of the things, or at least some of the content myself. I probably won't because I'm trying to focus on all this stuff. I will be a mentor, but not the way Bradley is. Like like the personal, the career development mentor. I signed up for that because they had some calls for that. So I'm looking forward to that too. I'm very limited. There were like a whole set of check boxes, and like, are you like in a PhD? Are you a neuroscience person? So I'm very much not many of those things, but apparently I was enough for this the one to throw some people at me and dispense, um, be an arena to talk about some managing career stuff, or maybe industry versus academia, or some other kind of mentoring things that we talked about here sometimes. So that should be fun. I think my first, it's like two, I don't even know, um, maybe somewhere between half an hour and an hour sessions at some point, that I'll be doing just small things, but I have a few ideas in mind and just conversations. But I think it's really cool. Like what I'm a big fan of Neuromatch. I'm always curious to see what. In some ways, I miss the early days where people were a little more trying to. But things are more structured now, and they can do more, and that's great. But I also I like the conferences and things like that too, and that was such a fun time in spite of the pandemic horrors. But I'm really curious to see what this latest round of things is, and one thing I always liked about them is they always. I think Neuromatch is a great spot to see what are people who are trying to push a lot of things forward in academia doing, and how are they being aware of the needs for mentoring and communication, and trying to do some of the, I guess, synthesis work that I'm always kind of harping on recently. And I feel like they're endeavoring to do it. So let's see how it goes this time. And I'm curious, what Bradley and I and others will think after this this summer session goes. Let's see.
Yeah, I think that it'll be great. You know, no, I would like to revisit some of these too. And as you saw from the syllabus, they don't have a really strong focus on bio-inspired models. It kind of put some things on there, and there's a lot more you could put on that list of things,
Mm.
that are sort of potential models and how they relate to, because I mean there are a lot of bio-inspired models, a lot of modeling that isn't like sort of conventional AI or reinforcement learning or deep learning. So that'd be interesting as well. But okay, so let me share my screen again. Okay, so I don't know if we've gone over this. This is an interesting paper I ran across. This is from 2020, and it's interesting from the standpoint of what we've been talking about with sort of the history of machine learning, the history of like cybernetics and computational methods. So this is by Alexander Fradkov. This is the early history of machine learning, and so this is a kind of a take on the history of machine learning and his way of kind of summarizing this. So the abstract reads: machine learning belongs to the crossroads of cybernetics, control science in parentheses, and computer science. So this is, I guess, his take on where machine learning belongs resides in that area of intellectual history. So You have cybernetics, which of course is control science, control theory, but also kind of its own thing, and computer science. So it's like right there. No mention, of course, of statistics or neuroscience, but that's, maybe another paper. It is attracting recently an overwhelming interest, both professionals and the general public. It's in the talk of a brief overview of the historical development of the machine learning field, with a focus on the development of mathematical apparatus in the first decades is provided. So he talks about sort of the mathematics and some of these early aspects of machine learning. A number of little-known facts published in hard-to-reach sources are presented. So it means that we're going to get some pretty obscure stuff in here. So it talks about how there's a connection between cybernetics and computer science, or control science and computer science, or, there is this connection, whatever it is. And so, it kind of talks a little bit about that. Let's talk about the early years. So the origin of machine learning in its modern sense is usually associated with the name of the psychologist Frank Rosenblatt from Cornell, based on ideas about the work of the human nervous system, created a group that built a machine for recognizing the letters of the alphabet. The machine, called the perceptron by its creator, used both analog and discrete signals, and included a threshold element that converted analog signals into discrete ones. So this is, kind of cybernetics, but also, you could say cognitive science, I guess. But that's not brought up here. But also computer science, because it is a computational tool. It became the prototype of the modern artificial neural network, and the model of its learning was close to the models of animal and human learning developed in psychology. So parallel to the perceptron, of course, we had a lot of behaviorism and a lot of experiments in that realm, but also sort of the dawning of cognitive science, where we're kind of interested more in cognitive functions rather than stimulus response. But in any case, that's kind of where we are at that. Rosenblatt himself performed the first mathematical studies of the perceptron. And so then in the early 60s, several groups were engaged in the design and testing of learning recognition systems. General statements of pattern recognition problems were proposed in the 60s. And this kind of talks a little bit about this. In the papers Vapnik and Lerner, Vapnik and Chervanekis and Yakubovich, deterministic approaches were developed, while an Azerman probabilistic statement of machine learning problems were suggested. So, in the cybernetics paper that we're working on, or we have, there is this really early history of like statistics and statistical models, and different ways of kind of modeling problems, as probabilistic state machines, and Markovian systems and semi-Markovian systems. And those are all kind of part of that history of cybernetics. It's really kind of an interesting area. I mean, you can really do a deep dive into statistics, but there is this aspect of, how these statistical models are being developed alongside what cybernetics is doing, and then also alongside computer science. And so he gets into this mathematical formalism about developed algorithms of learning. And so this kind of gets into this very simple, I guess he says it's a simple example. Let's see. So let each object or image, which is if this set xk, shown to the machine be encoded by a set of real numbers. So you expose the machine to a set of images, you encode them as real numbers, and it's part of the set xk. And it is required to train the machine to recognize which one of two classes, A or B, this new object belongs. And so you basically take xk, which are these images, you train the machine on them so that they can recognize any image as part of one of two classes. And you define the classes through a label. And then let for certainty xk belongs to class A, or k1, 2, ka, and class B for k, a plus 1, n. So basically you have K and KB as the class members. That is, the objects have a membership function yx, such as yxk. So now each object in those classes have a membership function, which is, I guess it's some probability. It sounds kind of like fuzzy control theory or fuzzy learning or whatever, because in fuzzy learning you have this membership function that kind of determines the degree of membership in a class. It is assumed that for convex systems, xk belonging to different classes do not intersect. So for your standard convex system where you have convex relationships, classes don't overlap. That's kind of the basis of machine learning. You can build a discriminative model. Convex system, which is a system where a normal degree of variation and things, are sort of normally distributed. You can typically treat two classes as being separable. And you can do that using sort of a discriminative model where you can basically draw a line. And there's no overlap between the two classes. You can separate the classes with that line. So again, different sets do not intersect. And these sets can be separated by a hyperplane, which is this line that you're drawing. And that's the logic of sort of a separable or discriminative model. It means there are a vector of weights, W, Wt, and a number Wo, such as that Wxk. So that's where you have Wxk here, which is greater than 0. Thus, the problem is reduced to the approximation of the function based on its values of a finite set. So basically, you're trying to approximate a finite set. You're trying to find a function that fits that finite set. And that's separate from any other set that you can build. So you have these classes that are sets. They have some affinity to each other. They're separable from other sets. And that's what you're trying to achieve with this method. Gradient type algorithms for perceptron learning construct some of the separating hyperplanes. So you can do this with perceptron learning. You can, these are gradient type algorithms. And this is the result shown in these papers here. And so this can be done in a finite number of steps. So we should expect to be able to find this solution. And so this is interesting also with respect to cybernetics, because cybernetics, maybe more accurately control theory, but cybernetics suggests that, there's some form of data, that there's some form of learning. And the learning, of course, takes this form of finding sort of structure in the data set. And so we don't really think of this connection between statistics and cybernetics too much, but when we do, it's usually this sort of thing. And, we actually attribute this more to control theory, but it's interesting that cybernetics also sort of has this aspect to it where, you're talking about good regulation and you're talking about, feedback being sort of the, mechanism that allows you to find good regulation. So there's this connection there too. And so it kind of goes through some more technical stuff here. Another approach is to choose a vector of weights, W, in such a way that the corresponding hyperplane is a supporting hyperplane to the convex hull of the available set of vectors, so that the minimum distance from it to the convex hull of classes is maximal. So this is the idea behind the support vector machine method. And so, a lot of times papers will go through sort of the history and figure out if they can attribute to one person or another person. And that's what they're doing here. It is a historical fact, however, that in the same year, 1964, an employee of the Laboratory of Theoretical Cybernetics of LSU, Boris Kozanets, published another fairly simple recurrent algorithm converging to an optimal supporting hyperplane, and that's in Kozanets 64. So this is like, stuff from the Soviet Union that we probably are in the West aren't aware of as much, but this is what people were working on sort of in parallel. So there's a cybernetics aspect to the support vector machine, that's what he's saying. There are other, algorithms that, have historical roots in cybernetics. It's really interesting how some of these things kind of dovetail. Talks about stochastic approaches where you have this, so the above mentioned methods are based upon deterministic approaches where an uncertainty is modeled as an element of a bounded set. So in other words, you have a bounded set, it's separable, and then there's this uncertainty. So, how wide is the uncertainty? How much, this relates to the membership function. So how certain are we that these data points belong to these different sets? How confident are we in our classification? So then it talks kind of about how this whole deterministic approach is sort of the standard in the field, but many papers are devoted to the statistical approach, where you can go back to some of the roots of decision theory and communications, which of course is the roots also of control theory. The most systematic framework based on average risk and minimization was developed by this person here, who has brilliantly demonstrated that it encompasses a large number of algorithms proposed by different authors in special cases. So there's this connection between thinking about machine learning as a deterministic approach, but also as a stochastic approach, kind of going over the roots of machine learning and sort of communications, as we know, that's linked to cybernetics, decision theory, which is somewhat linked to cybernetics, and then things like risk minimization and optimization. And you see this in operations research and other areas. So there are links, of course, between early operations research and cybernetics as well. So this kind of talks a bit about like stochastic approximation. And then you have these, so choosing the cost function for stochastic optimization in an appropriate way allowed the author to design different classes of algorithms described previously in the literature, as well as a number of new ones. Convergence of the algorithms can be established based on the stochastic approximation scheme under conditions of convexity and bounded growth, JW, which is part of this. This is the target of the stochastic search. So this unifying idea here is in the formulation of the adaptation and learning problem in terms of a performance index, which is JW, which is the average of the cost function, QXW. So you have this cost function QXW, you have this term here at the end, and then you are basically integrating over X to find this performance index, which is an average of the cost function. So that's, and then the problem is formulated by finding the minimal value of JW, and then the solution for that is based on these stochastic gradient algorithms, which gives you the stochastic aspect of it. And so that's what they're getting at here. So that's another set of interesting results from early machine learning and cybernetics and operations research. Then he gets into this about the two winners of AI and the second boom of machine learning. So the first, I guess, boom of machine learning was back when, a lot of cybernetics and operations research was coalescing in decision theory. And then this other part here talks about the winters of AI and the second boom of machine learning. So in 1969, the book of Minsky and Papert was published, where some limitations for complexity of the problem that can be solved by perceptrons were established. Namely, the authors emphasized that perceptrons cannot represent some logical functions like XOR or not XOR. So this is where we have exclusive OR, not exclusive OR. So basically the idea is that perceptrons can produce outputs that can classify things, but they can't represent logical functions. And so this is a problem in computer science because we want things to be able to represent different logical functions. And so perceptrons can't do that. They can't, I guess the implication is they can't reason. Although I think the shorter term implication is that they're not computationally useful in the ways we'd like. So this is, where this kind of triggered the first AI winter. So this is where you went from 1969 to around the 1980s, middle of the 1980s maybe, where perceptrons kind of died or got put on the back burner, and nothing was really done. So of course we know that perceptrons are sort of the basis, maybe a couple steps removed from deep learning. And so, that was kind of put away because we couldn't figure out how these models could produce these kind of results that we want. This triggered a reduction of funding in AI research in the world for more than 2 decades. This period was later called the first winter of AI. But there was still work being done on complex learning algorithms of different types, just not perceptrons. Okay, so but during this winter, there was a lot of work being done. So maybe the term winter is misapplied because you had a lot of different types of multi-layer neural networks, for example, that were being investigated at this time. So in 1980, Fukushima proposed a hierarchical multi-layered convolutional neural network known as the neocognitron, and this is something that is, I think, probably not well known to maybe a lot of people, but it's an important advance because not only is it an technical advance, but it happened during this AI winter. A significant impact was made by the invention of backpropagation learning algorithms, and this was done by several authors in the mid-80s. So Rumelhart, for example. Although the initial ideas were proposed still in the early 1960s, so there were some sort of results that pointed us towards backpropagation as early as the 1960s. But in 1986, this was proposed in this paper by Rumelhart et al. Compared to a standard gradient descent approach, which we talked about, where you have the stochastic search and then you're trying to find a performance metric, the standard gradient descent approach updates all the parameters with respect to error simultaneously. Backpropagation first propagates the error term at the output layer, and then sends it back to the layer at which the parameters need to be updated. And then a chain rule is used to update parameters with respect to the propagated error. So this is something where you have basically a feedback mechanism between the output layer and the inner layers where you have these we need to make corrections to the model. Backpropagation had some drawbacks. Sometimes it fails in cases where the classes cannot be linearly separated. So this is what we were talking about before, these discriminant models where you have these two neatly separated classes. And this is in a linear sense, so this is sort of the easiest class of problems where you can separate those two classes. And in cases where you can linearly separate your problem, backpropagation is easy. But in cases where you can't, and that's most real-world data, then backpropagation has problems. So this is, of course, all sort of during this AI winter, and I guess backpropagation maybe kicked off a new wave of research because this is about the time when the first AI winter came to a close and people started to get funded again. So the success of backpropagation and other computational advances produced great hope for future successes. However, real successes were less than expected ones, and the investments in the area of machine learning decreased again until the early 1990s. So this is where, backpropagation was kind of seen as a hope, but it wasn't exactly the hope that they needed. And we really had to wait until the early 1990s to get really a good, robust restart on AI funding. So this was I guess in the mid-80s there was some excitement, and then research funding declined until sometime in the early 1990s. So this is the second winter of AI. Nevertheless, an interest in studying neural networks is an instrument of machine learning. It was growing in the 1990s. So this is where we get this breakthrough, the Cortez and Vachnik paper. This is where we get the new version of our SVM algorithm and support vector machine algorithm for the general non-separable case. So this is where we don't worry about the separable case, we worry about the non-separable case, or where our categories overlap. And so this is where this was introduced, and under the name support vector networks. So support vector networks instead of support vector machine. And this is something that led to sort of this advance in being able to analyze data that's not sort of almost like a toy model of data. Something that's not completely convex, that has some, non-convex aspects to it. It has been widely used and been shown to be effective in practice. The algorithm and its theory has had a profound impact on theoretical and applied machine learning and inspired research on a variety of topics. Then there's this gold rush of machine learning. So this is where we're now seeing this sort of, or at least we saw this gold rush of machine learning in the late 90s and 2000s, where we're getting sort of these different trends converging. So 3 synchronous trends emerged at the same time. The first trend is big data. So, having a lot of data available so you can train the models. The amount of data became so big that new approaches were brought to life by practical necessity rather than the curiosity of scientists. The second trend is to reduce the cost of parallel computing and memory. So this, kind of developed with the hardware, but also with the software. So Google unveiled its MapReduce technology in 2004, which is, of course, software, followed by its open source counterpart Hadoop in 2006. And together they made it possible to distribute the processing of huge amounts of data between processors. So NVIDIA, a little bit later, came out with their GPUs. And so this is the hardware aspect where the GPUs were, allowed for this type of better processing to happen. So, and at the same time, the cost of RAM significantly decreased, which opened the possibility of working with large amounts of data in memory. And we ended up with new types of databases, including NoSQL. And so in 2014, then, the Apache Spark framework for distributed processing of unstructured and weakly structured data appeared. So all these things kind of improved our ability to run these models and to develop new models and modified models from this basic sort of set of approaches that were sort of the subject of the last few decades before this time. So this is from about 2004, maybe the late 90s to the mid 2010s. So and then the third trend is deep machine learning. So this inherits the idea of the perceptron, and as the author says, in combination with a successful scientific PR campaign. So that means that there was this, they had to resell the idea of the perceptron to people, but they also developed these deep neural network architectures, which took the perceptron and built, more sophisticated basis for it. It is believed that the term deep learning was proposed in 1986 by Rena Dechter, although the history of its appearance is apparently more complicated. A detailed and preferably objective analysis of the events of this period is still waiting for its researcher. Different points of view on the deep learning controversy of the naming can be found in different places. So, and then it talks about Geoff Hinton. And so by the middle of the last decade, a critical mass of knowledge in the field of DNN was accumulated, deep neural networks. And as always in such cases, someone is broken away from the peloton. So that's like a bike breaking away from the pack. In this case, the leader was Geoff Hinton, a British scientist. In 2006, they published a number of articles on deep neural networks in Nature. And so this is where, kind of talk about like the Hinton approach, I guess. And so how there were a whole bunch of people who kind of came out of that tradition and developed deep learning into the juggernaut that it is today. And so this article ends with a discussion, kind of recapping this history. And this paper is an attempt to present a general control-related view of the issue in the historical perspective, and kind of giving us a view into sort of those first decades, 2 AI winters, and how that all relates to the development of machine learning going forward. And so this is, really kind of an interesting paper. I think it has a lot of themes related to control theory, cybernetics, statistics, and then these AI winters and all the trends associated with that. Jesse says, by practical necessity rather than curiosity is an interesting line. Yeah, it's interesting. It's kind of like saying that you're doing something for applied purposes, and that's bad. Instead of just like kind of coming to it through peer research. But yeah.
Did you I definitely, so I want a long-term aim, like I want to make a hub somewhere. I don't know if it'll be like a full working group, but I want to basically have a space concentrated for history of science stuff and cybernetics and stuff specifically. So I'd really like to see the paper and put it in there. But I didn't know if that, I want to get back to the practical quote, but also, did you see put the paper in cybernetics, or was that somewhere else?
I'm not sure I posted it in cybernetics. I could post it in cybernetics. I'll probably do
Wherever you want, yeah. But I'd be curious to see the paper, because I feel like that seemed like such a, it wasn't extremely, like the pacing of the paper as an overview for what happened looked really good.
Yeah.
Like compared to other papers that kind of tangent, like it seemed like it's pretty tight. It wasn't too long, at least unless I missed something, but it looked like it was a nice, like it feels like something I could very put in a curriculum for history of AI cybernetics, or to fit that kind of a very specific need that we come across on many angles. So it was a good. Definitely want to keep track of that paper.
All right. Yeah, I'll post it. Yeah, I think it was a little hard. I don't know if it was translated from Russian or something. It was a little hard to follow, but it basically did get into he got into the statistical, like kind of mathematical minutia, which is good. It's useful, but I mean, for like this kind of paper, I'd like to break that out and say, like, what is it about? Because I mean, you get into this technical argument. Oh, the reason we're doing the technical argument is because we're going to talk about sort of the difficulty of doing like non-convex stuff. Like we can talk about the very simple case where everything is very well defined, and I can just build classes from, a prediction, and it's easy to do. But the whole point that he's trying to make is that these AI winters were because the models that were built were not very robust. And so people, like when they started to look into them a little bit more, they're like, well, they're not really that good. We need to kind of come up with better models. And so the hype receded at that point. So
yeah, and even like in my degree program, like we would come across, like you're taught, like SVMs, and you're taught these things that are like, but it's a nice little context for like where, even in their like potentially initial, like where did they come up in it? And I always feel like that's nice. And then like zooming all the way out again, like exactly what you said about like why were there winners, and what, like also that there was stuff going on in the background still in the winters too that wasn't necessarily famous or popularized, but then what were the things that kind of let them come out now? And even to circle back to all the different points I want to make, but by practical necessity rather than curiosity, I think it's a really interesting line just to think about in terms of not I guess it's easy to say what I don't mean. I don't mean like, oh yeah, like there was this golden era where, not like the meme about the nature, the guy publishing in Nature, the guy trying to understand nature. I don't feel like that's not what I'm trying to say, just to make clear. Like, I don't think it's only the pure wondrous curiosity of science that led us down the golden path. Not so much that, but more realizing there was practical necessity to, okay, deal with the data and things there. But also now, like, it's really weird for me to compare that to now, because in the moment we're in now, there's a very different, well, maybe not very different, but it's what is practical and what is curiosity driven or what is sort of investigation driven is very different. The forces at play are the same, but also different. So there's more there, but yeah, it's interesting. It's a really interesting paper. So thank you for going through that.
Yeah, no problem. Yeah, I thought that was an interesting kind of approach to the history of this. And of course, you can define the history in different ways, right? Like history is not
Exactly.
like,
But
but oh, go ahead.
that's kind of the point of. I don't know if I'm going to make it. Like I don't know what to do with this yet, but like I really want there to be I don't know what to call it right now, a group of where these exactly what you were just getting, like you could define history in different ways. Like I'm much less interested in defining having a definition or a static take. I don't want to say here is the history of blank, whether it's cognitive science, which is sort of, I don't know. I feel like I can't say the term. The term always says it's like, am I being like ironic when I use the term, or do I mean it? Or like psychology is different. The DSM and psychiatry is kind of its own thing, and then like AI or computer science or machine learning. And I'm not interested in making it the definitive history, but much more what are the lenses to use and like this place to discuss what are those perspectives um, for their development and other like understanding, like those sort of like the language, like a language or just a space to talk about how do you have some fluency in the uh, like I don't know the classes of discussion that take place about these things. So I don't think this paper is like a definitive, the definitive history, but I think it's a great example, or as a nice or a useful example of one lens um, from it. And when you take from that vantage point or use that lens, here's what you can, here's a take. So yeah.
Yeah, I also thought the sort of discussion about cybernetics was interesting. Now,
Yes.
cybernetics, like you didn't talk about Wiener and all these other people. And in fact, there's a whole history of like Russian and Chinese cybernetics. We've talked about this that are kind of separate from like the
Mhm.
Western, whatever's going on in the West at the time. But the standard, the ratio club or whatever approach. But it's interesting how there are these themes in cybernetics that kind of are part of that. Like there's this interest in good regulation, or there's this interest in very large systems, like Gordon Pask and some of these organizational oriented types, that they're looking at these very big systems. They're or even Ashby, very
Mhm.
big systems. They don't have the data to like do anything with it yet, but they're building these models. So like with CyberSyn, you're building a model of an industrial national economy, and you're building this sort of infrastructure for like monitoring everything. But the data didn't really exist yet. It was kind of
Mhm.
like we didn't have the way to collect the data that would give you the type of feedback that you wanted. You didn't have that kind
Mhm.
of continuous monitoring. Nowadays, you may have that actually. We're getting close, I think, to some sort of a system where you could monitor, and they do this with traffic, where they can do it with traffic in urban areas, where you can monitor traffic flows, you can get the data, and then you can make decisions sort of in real time. So, those sorts of, it's almost like in cybernetics, you had a lot of ideas that were ahead of their time in terms of getting the data in place. And,
Mhm.
that that's an interesting theme, but also you had a lot of ideas that were sort of leading us to this, to what we would see in control theory later, where you had much more formalized methods for optimization, for looking at feedback, for looking at these other things. So it's really interesting how cybernetics fits into this.
I just had this really curious idea, and I don't know how to formulate it, but I'll ask and see if it leads to anything. And I want to use we just hit a really nice comparison of cybernetics with sort of broader, less defined things that were maybe less formalized or harder to formalize and didn't have the data, versus what will become control theory, which is much more formalized, but also more, I don't know, more something perhaps. And so I guess I want to ask, is there any, in your understanding of either, I don't even want to say history of science, or just, is there any language or way of discussing like degree of formalization that a field has achieved? Or is it, I don't like, not saying there's a way to measure it, but almost like, I don't know if there's, is it more, is it, I guess maybe something, another way to say it is there anything about a field, you could say, maturing and formalizing more, but also some fields just have different takes on what formalization is or how much it can be like precisely formalized. Some things are some things have to be more zoomed out and maybe less formalized. Is there any ways to talk about that you can think of, or just?
I mean, I don't know. It's like, I guess you could say, well, you could first of all define what formalization is for a certain field, like, or, there are different ways you can formalize something. So one is through terminology. The terminology is very constrained if you have like really standardized terms across different papers. And you can do this using like literature mining, where you say, okay, this term is used, and this term is used 6 different ways versus one way. And if those terms are consistent across the papers, I mean, that might be more sort of methodologically mature, rigorous, because everyone's operating from the same place. And sometimes that's not like the fault of the field. Sometimes it's just that the field is very diverse. But, they use that as an indicator. Another, of course, is mathematical formalization. So do you have a mathematical formalization for something? And sometimes it's just a matter of like people have an intuition, but they don't know how to formalize the math. Sometimes you have like rules or laws that you might want to implement in. Sometimes you have to discover those laws, so it takes time. So that's another form of formalization, is sort of the mathematics, or if you have rules or laws for things, and you can just use that by looking at what the state of the art is for the models that you have. And then, a third kind of way of looking at maturity is kind of like, like maybe if you can implement something in code. So a lot of things, say in cognitive science, one of the goals of cognitive models is like, can you take like a cognitive process like attention or memory, can you implement it in code and then simulate it so that you can say, yeah, this is basically how it works. We can do a simulation. It gives us a lot of information about like what we can't directly observe, and it predicts the data well. So that's another way, is through this sort of modeling and simulation, looking at the code. And sometimes other ways you can look at it are using something like algorithmic information theory or something like that, where you look at how, and this is mainly, I think, in computer science, where you look at how efficient the code is. So if you have like something that's implemented in code, how efficient is that code? Sometimes, it's like you can describe something in code, but it's very hard to understand the structure of it. So you just kind of write code until you get something to work. But sometimes, getting it down to a short description length is good too. Getting it into fewer lines of code. So there are a lot of ways you can look at like the sort of maturity and the formalization of a field. And again, even like the number of papers published, although that's not a great indicator, might also be a good thing, because you can get a sense of like how much people have really kind of explored a topic. If it's like 4 papers, it's probably not been explored too much. But if it's like 2,000 papers, that just might mean they're going off in different directions. So it's really not a good indicator.
Right.
But that's where reviews come in. So reviews will kind of summarize the state of things, and then you get this sense of how mature the field is.
Okay. Thank you for that.
Yeah, no problem. Okay, I don't know. Morgan had something to say. He turned his camera on. So.
Just getting settled back in the house. So
Okay, yeah.
yeah.
Great.
My phone was about to die.
Oh yeah.
So yeah, back home.
Great. All right, so I'm going to finish up here, and I thought that was a great discussion. I'm glad that I brought that paper up today. I have another sort of article, and this kind of relates back to NeuroAI a bit. This is from the SIAM news. So this is the Society for Applied Mathematics, and they usually have some pretty good stuff here. This is something called the geometry of the Neuromanifold. So this is an article, research article by Kathleen Kohn, and this is about this idea of a neuromanifold. So this is going to talk about neural networks, perceptrons, this sort of stuff. So it starts out, machine learning with neural networks works quite well for a variety of applications, even though the underlying optimization problems are highly non-convex. So we come to this term again, convexity. So convexity is, where if you think about like a surface, it's kind of like a smooth, a smooth curved surface. That's a convex surface. And convex surfaces represent problems that have sort of a normal distribution. They're kind of like normalized data. They have all the properties of sort of in distribution stuff. So it's like, if I use a standard statistical model, I can describe my data pretty well. Now, when they say non-convex or highly non-convex, that means that it's not that sort of smoothly curved surface. You can't represent things on a smoothly curved surface and say this is the mean, and the mean describes everything along its every axis of its variation. That we can just summarize things at the mean and be done, or summarize things with a mean with a standard standard deviation and be done. It's much more like something like if you've ever heard of a rugged landscape, where you have maybe multiple mean points, or you have minima that are local instead of global. That's what they mean by non-convex. And so they're going to have this distinction oftentimes, especially when you get into the statistics literature on convexity versus non-convexity, and it has to do with that sort of statistical distribution, whether it's something you can describe, say, with an in-distribution, Gaussian distribution, or like something that's going to have a lot of unique cases or out of distribution behaviors, or these sort of exponential distributions, and those may or may not even describe the data well. So there's a lot to learn in that area. But in this case, what they're saying is that machine learning works quite well for a variety of applications, even those that are highly non-convex. Yet, despite researchers' attempts to understand this peculiar phenomena, a complete explanation does not yet exist. So we don't know why machine learning with neural networks works in this way, why it describes different types of data really well. It's hard to say. We don't really know why. We just know that if we do our machine learning, use our machine learning techniques, we get an answer. So there's a lot of sort of theoretical work that needs to be done here, but also theoretical work. So a comprehensive theory will require interdisciplinary insights from all areas of mathematics. In particular, and at its core, this phenomena is governed by geometry and its interplay with optimization. So there's a lot of interesting work being done in geometric neural networks and in graph neural networks, quite frankly. Because graph neural networks deal with geometry quite explicitly. You have a graph topology, it has a geometry. And so that geometry then translates into the solution. And This is something, again, we don't know exactly the details of it, but it's an interesting area. So the neuromanifold, and this is the term that they're using here, is a key player in the optimization problem of training a neural network. So take a fixed neural network architecture, and that fixed neural network architecture parameterizes a set of functions, wherein each choice of parameters gives rise to an individual function. So this is where we have in this image here a neural network without an activation function. So we have these inputs x, y, z. We have our parameters a, b, c, d, e, which are the like from x to this hidden layer neuron, and then from the hidden layer neuron to the output neuron. So a and d are different parameters, or just these different paths through the network. So the parameters a, b, c, d, and e give rise to a linear function R3, R2 of rank 1, namely x, y, z, to this d, a, x, b, y, c, z. So you have this distributive aspect where you pair a with x, b with y, and c with z, and then you have your d and e. So you have d, which is distributed, and then e, which is distributed. And so you have each of these parameters which take in these different options. So this is what they're talking about here. So the set of functions is the neuromanifold of the network. So this representation here with this sort of distributivity is the neuromanifold of the network. For instance, the neuromanifold in figure 1 is a set of all linear maps R3 to R2 with rank 1 at most 1. So there's this mathematical representation you can build of this neuromanifold. The neuromanifold in the simple example is a well-studied algebraic variety, but it suggests several tough questions for real-life networks. And so those questions include the following. Number 1, what is the geometry of the neuromanifold? When we represent it this way, it only gives us this sort of algebraic description, but it doesn't give us any sort of like geometry or geometric information, which is of course important if we want to map this to a convex or a non-convex space. We need to describe where this resides in this manifold, which is a manifold is just a surface that describes the data. So our convexity would be this smooth curved surface that describes where all the data sits on that surface. And then the surface describes variation in the data. So you go from the mean at the peak of this convex space to like variation that goes down the sides. And so, but we can describe it smoothly, so we can describe all the points. It's easy to understand that geometry. A non-convex surface might undulate quite a bit, might have a lot of peaks and valleys, and it's very hard to describe that just and reconstruct it just from observing data. So that's the understanding. So it's easy to interpolate the convex space, but not easy to interpolate the non-convex space. Okay, so these questions are: what is the geometry of the neuromanifold? Then 2, what does it look like? So again, you want to know what the geometry is, but then what does it look like in sort of this? Can we visualize it basically? And then 3, how does the geometry affect the training of the network? So if we know the geometry, we still need to know how it affects the training so we can optimize the training of the network. Let us explore another simple example of geometry's ability to govern optimization. Imagine the neuromanifold is a full-dimensional subset of Rn that is closed in the usual Euclidean topology. And that's in figure 2, which we'll get to. In a supervised learning setting, we provide some training data that is represented as a point in the ambient space Rn. Independent of the choice of loss function to be minimized, only 2 scenarios can occur during network training. So in this case, in supervised learning, where we provide some training data that's represented in a point in this space, we have 2 scenarios that can occur during training. So the first is that if the data point is inside of the neuromanifold, which is the thing that we're sort of trying to predict, trying to understand, then that point is the global minimum. Or, number 2, if the data point is outside the neuromanifold, then the global minimum lies in the neuromanifold's boundary. So it's basically like we can make a decision. It says data point inside or outside the neuromanifold. And then if the data point is inside the neuromanifold, then it's the global minimum. Or if the data point is outside the neuromanifold, then the global minimum lies in the neuromanifold's boundary. So this means that it's like either at the edge or it's the minimum. These scenarios can have practical consequences. If we can test a point's membership in the neuromanifold, and we talked about membership in the last paper where we talked about like if you have a data point that's in a set that is separable, it has a degree of membership or some membership criterion, right? So you don't know for sure maybe if it's part of one category or another. But in this case, you want to know if it's part of a neuromanifold or not. So if we can test the point's membership in the neuromanifold, we can hence reduce the number of optimization parameters by constructing a smaller network that only parameterizes the boundary of the original manifold. So this is an interesting approach because, you have this ability to say whether that point is either on the boundary of the manifold or the minimum. And then what you can do is say, okay, if I add in points, I can approximate that minimum or that boundary more specifically. So in either case, you can refine that surface of the manifold. And so as you keep adding points, you can make assumptions about whether it's the minimum. Because remember, you don't know what the global minima is. You don't know what the boundary looks like. Every time you add a point, it gives you more information about it. So that's what you're trying to do. And knowing something about that space or making some a priori judgments about that space can allow you to reconstruct it better. So in this case, the global minimum for data points inside the cylinder over the disk will be in the relative interior of the neuromanifold. And you can see this in figure 2 where they show this sort of dark orange space and this point is being added. And you can have it in this volume, which is, this lower dimensional subset, which is this dark orange. And you can see the points being added. It's either a minimum or it's on the boundary. And you can eventually sample more and more points and sample more and more of that space and define it better. So this kind of gives us some information. When we alter the loss function, the cylinder changes its shape, which can be challenging to understand. So depending on our loss function, we actually change the shape of this space because our loss function is going to determine, how this space looks. So we don't know kind of with gradient descent, when you explore gradient descent, you evaluate the points, you determine your loss function. So the loss function is always moving towards the minimum. And so when we alter the loss function, we alter the shape of this unexplored manifold, which is, of course, there's an interaction there. And it's kind of like in fitness landscapes, when you alter when organisms always alter their fitness over time. They're fit at one point in time, and they're more or less fit at another point in time. And that can alter the fitness landscape topology, which is a similar thing here. But every time you keep sampling points, it changes the loss function. The cylinder or the space, the manifold changes its shape, and then it's just hard to really kind of get a handle on the true shape. And maybe it is that, the manifold just kind of changes shape as you explore more and more of the data, which is even more depressing because it really makes it hard to approximate it. And of course, that's all we can do is approximate the space. We can't understand it in its totality. So there are a number of interesting questions there. The boundary points of the neuromanifold are not the only interesting points that become more exposed during training. So we have the boundary points, of course, we have the minima, but a neuromanifold often has singularities, or the points at which it does not look locally like a regular manifold. So this is where, you have a manifold in its totality. We're used to thinking about this in terms of embedding these points in a space and knowing the space, having global information locally. But a lot of times when you're at a certain point, or especially when you have only a few points, or when you have sparse data overall, it's not going to give you basically the full information about that manifold. So when you're only at, when you only have a few points, it's not going to look like the regular manifold. It's going to look vastly different. And so, this is something that's really interesting. So for instance, imagine the neuromanifold is the plane curve in figure 3. And so this is down here, which has one singularity, a cusp, which is defined, I think, here at this bright red point. Okay, so we have this cusp point. Figure 3 illustrates the data points whose global minimum is the cusp during the minimization of the Euclidean distance. This set of data points is a positive measure, which means the cusp is the global minimum with a positive probability over the data. On the contrary, any other fixed non-singular point on the curve is the minimum with probability 0. So this is like the point that's the minimum. Everything else is not the minimum because it's right at the point. It's sort of the minimum. There's a geometric aspect to this. So for any point within the pink region here, the unique closest point on the purple curve is the red cusp. So we're comparing this pink region here in the middle with this purple curve. Because this purple curve only overlaps at this one point, it's a singularity with respect to this description. So you can actually characterize this quite well as a geometric problem. So in the context of these optimization properties, an additional layer of complexity arises because the network training does not occur in the space of functions where the neuromanifold lives, but rather in the space of parameters. So different networks can yield the same manifold, but they parameterize that manifold in distinct ways. Such parameterization often induces spurious critical points in parameter space that do not serve as critical points of the neuromanifold in function space. So this is interesting stuff with respect then to moving towards networks and some of these aspects. Among the easiest network architectures to study are fully connected linear networks. This is the standard sort of workhorse of network science where we want to characterize sort of a random network or something that's a comparator to some network structure. This architecture has no activation function, and all neurons from one layer are connected to all neurons in the next layer, so there's this fully connected aspect. As in figure 1, the neuromanifold of such a network is an algebraic variety, a solution of polynomial equations that consists of low-rank matrices. It's a very easy problem. Though it has no boundary points, it does have singularities. Depending on the loss function, these singularities can be critical points with positive probability. And so along with these spurious critical points in the parameter space, they play a crucial role in the analysis of the convergence of gradient descent. Okay. So that's kind of talking about kind of linking network architecture with some of the ways that we analyze them, or we do our analysis, and then having these spurious critical points in parameter space, and then looking at the convergence of gradient descent. So how does gradient descent happen with respect to some of these geometric features and some of these parameterization aspects? Okay. In the linear convolutional network, not all neurons between neighboring layers are connected. So this is where we have this it's not fully connected. There's a sort of selectivity of connections. And several edges between neurons share the same parameter. So each edge is sort of a parameter in this network. So if you think about like networks with a really high number of parameters, all it is it's just the connections between neurons. So when you have a lot of connections, when you have a fully connected network that has a lot more parameters than one of these networks that are selectively connected. But the selectively connected networks, I guess have less predictive power. So in the linear convolutional network, we don't have this full connectivity. We have fewer parameters. But sometimes several edges between neurons share the same parameters. So we have the sort of condensation of parameters. More concretely, this type of network parameterizes linear convolutions that themselves are composed of many individual convolutions, one for each network layer. So this is figure 4 where they talk about this filter. This is, they say here, for instance, a linear convolution of one-dimensional signals is a linear map wherein each coordinate function takes the inner product of a fixed filter vector with part of the input vector, and that's C figure 4. So this describes this overlap in these filters, and this kind of describes how these share parameters. So this yields a linear convolution. So if you have this overlap of these three filters, these overlap areas of linear convolution because they're convolving the signals. So when you share a parameter, you're convolving the signal. And then, so they talk a little bit about convolutions and their role in neural networks, and that's equivalent to the multiplication of certain sparse polynomials. And unlike the fully connected case, this network's neuromanifold is typically not of algebraic variety. Instead, it is a semi-algebraic set. So this is where the solution set of polynomial equations and polynomial inequalities, and you go back to the disk in figure 2, and you can think about like that set of solutions for these polynomial equations, and how that exists in a semi-algebraic set. Moreover, the neuromanifold is closed in the standard Euclidean topology. It typically has a non-empty relative boundary, whose relevance for network training depends on the network architecture, and particularly on the strides of the individual layers. And so this kind of goes through some of this. Let's see, in conclusion, we can drastically change the geometry of a neuromanifold by varying the architecture of its neural network. So this is interesting that there's this connection between this geometry of the manifold and this architectural, varying the architecture. So basically, when you reduce the connectivity or you change the connectivity, you're changing this manifold, you're changing the number of parameters in the model. For the simple architectures that we describe here, the neuromanifold is a stratified manifold that consists of low-rank matrices and tensors or reducible polynomials. Its geometry governs the optimization behavior between network or during network training. So the geometry governs its optimization, so there's a link between the geometry and gradient descent. We have demonstrated the impact of replacing fully connected layers with convolutional layers. So these fully connected layers are where we basically have one connection and it's one parameter. The convolutional layers are where you have shared connections for the parameters like we discussed. So we have these fully connected layers and convolutional layers as these two aspects of the network. So we've replaced these two in linear networks. We've demonstrated the impact of doing that. Future work will reveal the corresponding effect of nonlinear networks. So this is where we have to get to the nonlinear case, which is, we assume it's more interesting. Interested researchers can use algebraic-geometric tools, which is in the second citation here, which is metric algebraic geometry, and to explore algebraic activation functions such as the rectified linear unit, which is citation 8, tropical geometry of deep neural networks. And so there's a lot of interesting work in geometric neural networks that I'm not mentioning here, but it's really kind of an interesting direction. The study of other activation functions will require analytical techniques and collaborations between several mathematical areas. So that was pretty heavy mathematical deep learning or mathematical stuff, but there's a really interesting set of things that are going on there. So yeah, Jesse had to leave. Thank you, Jesse, for attending. And I think that's it for that article. Now, do you have any comments or questions, Morgan?
No, I mean, those are kind of so many techniques try to exploit the let's find the reduced form in I'm thinking more from data analysis standpoint, from the kind of more theoretical,
Right.
But so many of our techniques are assuming that there's a submanifold that can be determined algorithmically somehow. or that reduced form is would be useful, you know, and just thinking of more analysis pipelines that exploit that, and then the importance of mathematical importance of differentiability, and, which is what the problem of the singularity, right? And there's excuse me, someone had this very long paper that they published July 4th, that was like using PyTorch and JAX and talking about all sorts of architectural features, but it was called Alice's Adventures in a Differentiable Wonderland. That I did like the name, but
Did you post that in the Slack? I think you may.
I didn't. I totally. I can.
All right. Yeah, that would be great.
I thought it was good. There was. I'm trying to think of some things that I know I meant to add to Slack. I'll drop that in data ML, data SciML.
Okay.
There's and I thought that was pretty good. Yeah, there's a UC Berkeley course in large language model stuff is also in there. Oh yes, but just one thing. I know we're kind of out of time here, but in Dev AI, this why do children and adults learn differently?
Oh yeah.
That just another, again, another reason to study developmental psychology. There was an interesting paper on Hacker News that was like from 1985, and it was talking about. So it was like more an educational psychology paper.
Yeah.
Where they were talking to kids. Remember, this was the time of logo,
Oh yeah,
the right language, and so they were teaching classes of kids logo, and then they were kind of debriefing them afterwards, and which is already problematic.
Yeah.
Right? So I mean, but again, like super interesting for developmental psychologists. Like, how do you get insight into how kids think? Right? But they were talking to them about recursion in logo. Like they gave them a particular problem, and we're teaching them this algorithm. And then we're kind of asking them about it, and they noted that there was this real problem with the kids. Like the kids seemed to get the wrong idea about it, and this there was this typical psychological problem of the kids held this view about it. Even in the face of evidence, like it seemed very resilient to being counterfactuals or something like that.
Yeah,
right?
It's kind of like
and the anyway, there was somebody was talking on the internet about this difference between how children and adults learn, and of course that it's naive to think that that's a weakness, or like again, like all these things have their place, or kind of like like again, we're not we really need to see the big picture before we say this is a problem, because what we certainly know is that kids aren't learning everything rote.
Right.
and there's some incredible induction going on, and so it's just important to note that like not everything that us adults, the ways that we're thinking is what's happening for young developing systems. And I thought that logo example was interesting.
Yeah, it reminded me kind of I've seen a couple talks where they talk about naive physics. This is where the physics where children will learn physics just kind of from interacting with the world, and then later they learn about the rules, like the laws of physics and things like that. But you get like this naive physics that develops before there's a more formalized physics. But still it's interesting because it's like if we were training a robot, how would it learn physics? It would learn through interaction. But that's not really like, there are a lot of things that it kind of doesn't do in the same way that we have as from a formalized physics, which is having laws. And so we could train a robot on like laws of physics, or we could train it by having it sort of pick up these naive rules or these naive ways of thinking about the world. And so it's very different kind of training regimen.
Right. And that how important it is to again remember that what we're actually dealing with are continual learning systems, and not kind of a single system, right? That's supposed to get everything right. So it's again, if it's only when we see this as a multi-step or multi-phase process that are we going to start to see why, like these early naive stages are perhaps really important, because again this is in a much larger context of multiple critical periods and multiple representational redescriptions, because we don't get to have a neural net for each of these things. That it's just one. We have one brain that's trying to bring all this in and create interfaces between it all. Anyway, it was nice to see. My undergrad psych was cognitive development, so it was a good reminder of this. Anyway, you can find that at DevAI.
Okay, thanks. So this paper, why do children and adults learn differently? What was the basic?
This was more of just they did a symposium. Okay. Like I think there was a speaker that this particular woman is like a brain imager. Like babies and children are fast learners, right? So it's like, again, it was just kind of getting at these, what are the mechanisms by which they're able to do all these things, right? That seem kind of superhuman, right? Well, there's Thomas Elbert. I recognize that name. But yeah, it's a list there. This was like a symposium though. Hector Fellow Academy. I haven't heard that. But then in what was the other one? Well, I'll find this logo paper that was on Hector's. Yeah, that was interesting. Also, just nice to a blast from the past in 1985.
Oh yeah. So I wonder, I guess with kids it wouldn't matter so much, but I wonder if if you had people who knew what a concept was, more like if it penetrates sort of the popular imagination more versus something. Because in 1985, I'm not sure how much recursion was a part of sort of the popular imagination. I mean, personal computing was rather new, and so it would be like, well, what is recursion? And then you'd have to describe it, and people wouldn't have a real frame of reference for it. I mean, nowadays it's a little bit more obvious because more people know programming. It's more part of like the world. So I'm just curious as to.
Well, yeah. I mean, I'm curious too. Well, one, I'm curious if maybe something like this is why it's been harder to break to start computer science classes earlier, or like there's just some interesting things about computer science education that have been controversial, and so I don't know. I mean, it's hard for me to think back to this time. I mean, I don't know if you were like this, but I was one of those kids that learned computers, at 8 or 10 because I had a little hobbyist kid, and so it was very much like experiments I was, in a sense, experiments I was doing on my own, right? It probably would have been better if I'd had a teacher or something. See, I'll put this in Divya. Yeah. So it would be interesting to see if the Raspberry Pi Foundation has a seminar series on kind of like education of computer science education, theory, practice, like a combination of both, that tries to get educators to talk about like the difficulties as well as strategies, but I think in this case, and this was more the age range, it's like this younger age range is certain, even in Piagetian sense, right? Like they don't think like us, and it's a mistake to kind of rationalize your educational strategy in the same way. But that can be hard to do. And this was my thesis work was again like Annette Karmeloff-Smith kind of work, where it was you were doing experiments to try and get at how that age range thinking was fundamentally different. Anyway, it would be interesting.
Yeah. Well, that's great. Yeah. All right. Oh, go ahead.
No, it's a good question. Like I haven't looked at it, but yeah, all that kind of algorithmic or computational thinking is kind of new educational psych to consider.
Yeah, food for thought. All right. Well, thanks for attending, and it was a good meeting, and see you next week.
Take care.
Take care. Bye.
See you.